Hello, in this video I'd like to talk about some undecidable extensions of the regular structures that we've been looking at so far. Remember that the key structures that we're interested in studying in this video series are the word logic, the weak second order theory of one successor, and Büchi arithmetic. And they're all expressively equivalent to each other, and they're all expressively equivalent to the regular languages. So what sorts of things can we add to these structures to make them undecidable? We've already seen that when we add multiplication onto Presburger arithmetic, that is the structure which is just the natural numbers with addition, it becomes undecidable. So what other sorts of extensions can we make? What other things can we add to our structures to make their first order logics undecidable? And to start, I'd actually like to talk about some extensions to Presburger arithmetic. Remember that Büchi originally believed that if you added a predicate that just recognized powers of 2 onto the structure of the natural numbers with addition, that the resulting structure was expressively equivalent to the regular languages. It's not, it's slightly weaker, but this is still an interesting topic to study. So suppose that we're studying the first order logic of Presburger arithmetic, which is the natural numbers with addition, with an additional unary predicate p. So we have some sort of, we feed it in a natural number and it tells us true or false. And really what this winds up corresponding to is some set of natural numbers, right? The set of natural numbers that make this predicate true, and then there's all of the other natural numbers that make this predicate false. We know what happens if this predicate winds up corresponding to the powers of 2. The resulting structure winds up being slightly less expressive than the regular languages. But there are plenty of other questions we can ask. What happens if this predicate recognizes primes? Well, then we can phrase in the first order logic of this particular structure all sorts of open problems about prime numbers, such as the twin prime conjecture. So having an algorithm to decide if those formulas are true would give us an algorithm for solving a whole bunch of open problems in number theory. Or you could view that in reverse and say, in order to be able to find an algorithm for determining whether or not those formulas are true, we would need to first solve a bunch of open problems in number theory. But something really interesting winds up happening if our predicate winds up corresponding to the squares. So our predicate is true of those values of y for which there exists an x such that y is equal to x squared. So for instance, we say that p of 5 is false and p of 9 is true. Note that on the surface, this doesn't give us the ability to ask, what number is this a square of? Right? We know that 9 is a square, but we don't know that 9 is a square of 3. We can't, just using addition, well, it's not obvious how we could, just using addition, say that 3 squared gives us 9, given the fact that 9 is a square. Right? So there's a slight difference here, right? There's the ability to say that one number is another number squared, and being able to say that a number is a square, but we don't know what number it is the square of. But actually it turns out that this is enough to be able to say that one number is the square of another number. If we have a square number and we want to figure out what it is the square of, all we need to do is look for the next square number, right? We can talk about less than in this particular language, again, because we have the natural numbers with addition. All we need to do is find the square which is larger but has no squares in between, and that gives us some number a squared and a plus 1 squared. And the difference between a and a plus 1 squared is going to be 2a plus 1. So we can recognize what square we're looking at just by looking at the next square and trying to figure out how far away it is. That gives us this particular formula here for representing the formula y is equal to x squared using just this predicate here. Once we have the ability to talk about the square of any particular number, this gives us full multiplication, given the fact that we already have addition. All we need to do is take a look at x plus y squared. This number here, we can then subtract off x squared and subtract off y squared. Remember that we can talk about subtraction in our language, provided that we're not subtracting something that's larger than something else, because we don't have negative numbers. But this is perfectly fine. X plus y squared is always going to be greater than x squared plus y squared. This result here is going to be equal to 2xy. And so if we wanted to say that z is equal to xy, we would simply say that z is the number which, when you take 2z, when you take z plus z, gives us this result here. More specifically, we can say that z is equal to xy if x plus y squared is equal to z plus x squared plus y squared. And so what we can do, if we have any sort of first order logical formula in the theory of full arithmetic, in the theory of the natural numbers with addition and multiplication, we can use this and possibly some relationalization in order to turn that formula into a formula just involving the natural numbers with addition and this predicate that just recognizes squares. And so in order to have a decision algorithm for this structure here, we would need a decision algorithm for the full structure of the natural numbers with addition and multiplication. And we don't. That's undecidable. So this structure here is undecidable for the same reason. We can use it to talk about Turing machines. It's just a really complicated process to get to talking about Turing machines. A very similar proof works in the case that P recognizes the range of any degree 2 polynomial with integer coefficients whose limit as n approaches infinity is infinity. Things get a little bit tricky when reasoning about these sorts of polynomials because we don't have the full integers, but it's not such a big deal. All we need to do is make sure that the polynomial doesn't have a finite range over the natural numbers. If we have a predicate that's only true for some finite number of things, we can just write that predicate out in the theory of the natural numbers with addition, right? Adding in a predicate that only recognizes finitely many numbers isn't actually going to add anything to the expressiveness of the structure. It's going to be just as decidable as Presburger arithmetic was. And I'll let you figure out how to adapt this proof for arbitrary degree 2 polynomials that actually have an interesting range. But the thing that we can do with this then is increase the degree of the polynomial. Suppose that we have a higher degree polynomial with integer coefficients q, and P recognizes the range of that polynomial, and this is actually an interesting range. The limit of q of x as x approaches infinity is in fact infinity. Then eventually consecutive elements of this range here are going to be consecutive outputs of q. This isn't going to happen right away. Q can oscillate a whole bunch because it's a polynomial, but eventually it's going to start going off towards infinity. And at that point, when it surpasses the maximum of all of these oscillations, it's going to wind up being the case that q of x plus 1 is larger than q of x, and there's no element of the range that's in between the two. What this means is that if we define the polynomial q prime of x to be q of x plus 1 minus q of x, the discrete derivative of q, then in our logic we can recognize the range of this polynomial for sufficiently large x, for these large enough x. We simply take the difference between consecutive elements of the range of q. Then by adding in a bunch of discrete exceptions for the smaller cases, we can wind up representing the entire range of q prime. Q prime is going to be 1 degree lower than q, and so what we can do is we can continue this process until we have the ability to recognize the range of some degree 2 polynomial, whose limit as n approaches infinity is infinity and has integer coefficients, And then we can use that to describe multiplication. So all in all, if we start with Presburger arithmetic and then we add a predicate that recognizes the range of a polynomial with integer coefficients whose limit as n approaches infinity is infinity, it winds up being the case that this structure is undecidable. It's capable of expressing multiplication, and because it can express addition and multiplication, it's capable of expressing Turing machines. Let's change tracks for a moment and talk about extensions of the word logic. Remember that this is the structure whose elements are words on some finite alphabet, and it has an equal length relation and a prefix relation and operations that tack particular letters onto the end of words. And let's think about what would happen if we added on the thing that we would really like, which is concatenation. And actually, let's take out some of the pieces so that this isn't such a complicated structure. We're just going to be talking about the words on some finite alphabet sigma with concatenation. And I also need to add in special constant characters for all of the different letters of the alphabet. These constant characters represent words of length 1, which is just that one letter. In the first order logic of this structure, we can talk about one word being a prefix of another word, or being a suffix, or being a subword of another word. It turns out that the first order logic of this structure is undecidable because it has the power of full arithmetic. One easy way of representing arithmetic in this structure is to represent the number n by the word, which is just n copies of the letter A. And in this case, concatenation is going to correspond to addition, right? If we have n copies of the word A, and then we concatenate on m copies of the word A, well, that's going to be n plus m copies of the word A. And so this structure, with this particular representation, can already talk about addition. Let's show that it can talk about multiplication. The particular proof that I'm going to show you assumes that sigma has special characters. A left angle bracket, a middle bracket, and a right angle bracket. And you can make this proof work without these special characters in the alphabet, simply by using really long sequences of one particular letter in their place, right? So we could have, let's say, b to the n for some really large n, larger than all of the other words that show up as part of the construction, and that can represent each of these characters. It's a very clever trick, but it makes it a little bit harder to see what's going on in the proof, so I'm just going to assume that we have these three special characters that we're not using elsewhere. We can use these special characters to represent pairs. We'll say that z is the pair of x and y if z is equal to left angle bracket x, middle bracket y, right angle bracket. And of course, technically there should be concatenation symbols between all of these, but that's just going to make it harder to read. And x and y don't have any of these special characters in them. Merely having the ability to talk about pairs in this circumstance allows us to do recursive constructions. So here we have a recursive construction for length multiplication. If x is a series of a's and y is a series of a's, then z is going to be a series of a's whose length is the product of those two series of a's. And this argument is going to be a lot easier to see if I just identify x. We can treat x as a number, and we can talk about x as a number. We'll just identify x with the length of x, right? The number of a's within x. And having this identification allows us to say, okay, we're talking about x times y is equal to z, instead of the more complicated z is a sequence of a's whose length is the length of x times the length of y. It's just going to be easier to say that x times y is equal to z. So we're going to say that this is true if by definition, for any word W, and we're going to want to treat W as like a set of pairs. W being a word is just going to be this really long sequence of random characters, and within that sequence somewhere is going to be a bunch of pairs, a bunch of things that look like this, where X and Y don't have any of these special characters in them. And it's important that X and Y don't have the special characters in them. If we're going to put a bunch of them together into a word, we could have something like this, and we can view this as an opening bracket followed by a sequence of characters, followed by a middle bracket, followed by this as the second term in the pair, followed by a closing angle bracket. And we don't want to view it that way. We want to view this really long word as a set of two pairs, as opposed to one really long pair that has this complicated thing in it. So it's really important when we talk about pairs that X and Y don't have these special characters in them. So we have this word, and this word, again, is just going to be this random sequence that has some pairs within it. And the pairs that we're going to want to be in W specifically are going to be pairs of the form P comma Q, where Q is equal to X times P. And we're going to be a little bit loose about this because we can't talk about having infinitely many pairs because W is only a finite word. So what we're going to do is we're going to say that if Y comma Z is a subword of W, I'm going to use subset to mean subword. That is, it shows up somewhere within the word as a consecutive sequence of characters. You can describe this using concatenation. If Y comma Z shows up as a pair within W, and for any time P plus 1, right, the successor A of P represents the number P plus 1, comma, Q plus X, remember Q concatenated with X represents Q plus X, every time this pair is within W, then the reduced pair, so we go from P plus 1 to P, we go from Q plus X to Q, we subtract 1 from the first coordinate, we subtract X from the second coordinate, is also going to be in W. Anytime that we have this, and we're downwards closed in this particular fashion, then we're also going to have 0, 0, right? The empty word comma the empty word as a pair showing up within W. Now, W might have a whole bunch of red herring pairs that aren't part of a descending chain starting from Y comma Z, working its way all the way down to 0 comma 0. But all we need to know is the fact that if Y comma Z is in there and we're closed under this subtraction operation, then 0, 0 is also in there. And because we have this, this enforces that Z is equal to X times Y. The key idea is that if we start off with a pair where X times Y is equal to Z, and then do this reduction process, we're eventually going to get 0, 0. But if we start off with a pair where X times Y is not equal to Z, then doing this reduction process will ultimately result in a pair that isn't of this form. And so it's not necessarily going to be the case that this pair shows up within W. It might anyway, just because W might contain a whole bunch of extraneous pairs, but it isn't necessarily the case that 0, 0 is going to show up somewhere within W. So this gives us the ability to talk about addition and multiplication within this structure. Again, we don't actually need these special characters. We can just rely on really long sequences of B's that are longer than any other letter that shows up within the argument. So we can talk about addition and multiplication in this structure, but really what's going on in this construction here is it gives us some sort of idea about how to do recursion. Right? We can replace this Q concatenated with X by some other function and maybe fiddle with the argument a little bit. I'm taking advantage of the fact that this operation is invertible, but ultimately this kind of describes how we can talk about recursion in this particular structure here, the words with concatenation. And again, remember it was the recursion that Gödel's beta function allowed us that made the structure of full arithmetic, the natural numbers with addition and multiplication, undecidable in the first place. Let's take a moment to look at weak S1s where we add in addition. Remember that when we were showing that weak S1s is expressively equivalent to the regular languages, we encoded finite sets of natural numbers as words, as sequences of A's and B's, where there were B's in positions whose indices were in the set. So for instance, we could encode the set containing the numbers 0, 1, and 3 as BBAB. There's B's in positions 0, 1, and 3, and there isn't a B in position 2 because 2 is not in the original set. Let's toss in another set. Let's say 0, 2. Then if we want to describe the concatenation of these two words in the corresponding language of weak S1s, all we need to do is take these letters and shift them over so we can slot them in up here. The concatenation of the two, BBAB, BAB, is just going to correspond to this set of indices, and then having B's in indices 4 and 6, which is just 0 and 2 shifted over by 4 units. And all we've done here is we've added 4 to each element of this set. Well, if we toss in addition into our language, we can talk about doing that. We couldn't talk about doing it before because we didn't have addition. But now, if we toss addition into weak S1s, we can add 4 to all of the elements of this set, 4 being, in this case, 1 more than the maximum element of this set, and then take the union of the two, and that's going to give us the set corresponding to the concatenation of the two words, specifically 0, 1, 3, 4, 6. And so tossing addition into weak S1s effectively gives us the power to concatenate words together. And you can formalize this process to show that this structure here is also undecidable because you can use it to write out sentences in the structure of words with concatenation, which you can use to talk about addition and multiplication, which you can use to talk about Turing machines. Instead of adding addition onto the weak second-order theory of one successor, I mean, there's already a lot going on. Addition seems like a really powerful addition to this particular logic. Let's instead just add a multiplication by 2 operation. Just like when we were talking about words with concatenation, we're going to want to be able to talk about sets of pairs. And, well, we have sets, but these are just sets of numbers. How can we represent a pair as a single number? Well, there are many such functions, but the one that we're going to use in this proof is j of xy is equal to 2 to the x times 2y plus 3. This is one-to-one. This is unique, right? If we have a particular pair, there is going to be a unique natural number that encodes it. And we can't talk about this directly, but we'll be able to, using codes, be able to talk about these numbers here. Of course, this is unique by the uniqueness of prime factorizations. If I have a number, I just take its prime factorization. I look at the power of 2, that's going to give me x. And hopefully there's only one other factor, and that factor is an odd number, and that's going to give me y. And we'll call the numbers that we construct in this way codes for these particular pairs, just for clarity's sake. It's helpful to be able to distinguish between numbers that are meant to represent pairs and just numbers by themselves that maybe we want to be elements of pairs. In our language, we can describe when a code has a particular second coordinate. I'm going to call this function the projection onto the second coordinate. And we'll say that the projection of z, which encodes a number, is equal to y, which is a number that's part of a pair. And we'll define that happening when for any set B, if z is in B and B is closed under dividing by 2, whenever 2x is in B, x is also in B, then that necessarily means that 2y plus 3 is in B. And we can write this in this structure here. It's just going to be double of y, and then you take the successor 3 times. So what this is saying is that if we have a code in our particular set, and then we're also closed under dividing by 2, then this code with this number decreased by 1 is going to be in the set, and the code with this number decreased by 2 is going to be in the set, and so on and so forth, all the way down until when this is 2 to the 0th, in which case what's left over is going to be 2y plus 3. This expresses some element of the set being of this form for our particular y. It's going to be a little bit harder to get a handle on the first coordinate of a number, but it's very easy to add 1 to it, right? If we have a pair, we can increment the first coordinate. If we have a z encoding a particular pair, we can increment the first coordinate, increment x, just by doubling it. We can also, here's the clever thing, increment the second coordinate without changing the first coordinate. And this is the really tricky bit. We'll say that w encodes the pair that is z, but with the second coordinate incremented by 1, if the y-coordinate of z is n, for some n, and the y-coordinate of w is n plus 1, the successor of n, for the same n. So this means that their y-coordinates are going to be one more than each other, but how do we make sure that the x-coordinates are the same between z and w? Well, it turns out all we need to do is make sure that w is between z and 2z, and that suffices. And remember that we can talk about less than in the original weak second-order theory of one successor using prefix closed sets. As a further part of this construction, I'm going to want to be able to construct pairs of the form 0, y, and that's literally just 2 to the 0th times 2y plus 3. That's going to encode the pair 0, y, so that's just equal to 2y plus 3, which again we can create by doubling y and then taking its successor 3 times. It's helpful to think about these codes as representing points with integer coordinates in the first quadrant. And I'm actually going to introduce some notation to talk about the geometric relationship between two of these points. Specifically, I'm going to write z diagonally down arrows w to indicate that z represents a point which is diagonally above and to the left of w along a perfect 45-degree diagonal. This is going to correspond to the formula for any set B. If z is in B and B is closed under taking a step down and to the left, which can be indicated this way, then W is also going to be in the set B. We need to be a little bit careful about doing these constructions because we want to make sure that these sets being referred to are actually finite sets. But luckily, this particular construction, these sets B are just going to terminate when they hit the x-axis. We can use a similar construction to indicate when Z is directly above W. We simply say that For any finite set B, if Z is in B and B is closed under taking a step downwards, that is, every time when we increment the y coordinate by 1, that's in the set, then when the original thing, when we didn't increment the y coordinate by 1, is also going to be in the set. Then together, that implies that W is in the set. Again, saying any set which contains Z and is closed under taking a step by 1 unit downwards is also necessarily going to contain W. So finally, we can describe addition. We can talk about when A plus B is equal to C, if the point 0A is diagonally above Z at a 45-degree angle, the y-coordinate of Z is 0, W is directly above Z, the y-coordinate of W is B, and the point 0C is diagonally above W at a 45-degree angle. What this picture looks like is this. The coordinates of Z being diagonally below the point 0A at exactly a 45-degree angle and having y-coordinate 0 have to be A0. The coordinates of W being directly above Z and having a y-coordinate of B necessarily have to be AB. And finally, the value of C, in order for the point 0C to be diagonally above W at exactly a 45-degree angle, it has to be the case that C is equal to A plus B. And so simply by adding in the ability to talk about doubling into the weak second-order theory of one successor, we were able to talk about addition. And remember that addition allows us to essentially do the same sort of concatenation arguments that we were doing before, which allows us to talk about addition and multiplication, which allows us to talk about Turing machines, and so this theory is also undecidable. Finally, let's look at an extension of Büchi arithmetic. Remember that Büchi arithmetic was the theory of the natural numbers with addition and this extra operation v2, where v2 of x is the largest power of 2 dividing x. It's worth noting that if we replace v2 with v3 or v4 or v5, where those are, vk is the largest power of k dividing x, we also get a structure that's expressively equivalent to the regular languages. We just use a slightly different encoding, this encoding in base k, where it's vk that we're looking at. And so we might wonder, what happens if we have the same structure but with two different v functions in it? If we have v2 and v4, for instance, we haven't actually added anything. We can write v2 in terms of v4 and v4 in terms of v2. On the other hand, if we consider a structure with v's with incompatible bases, how expressive is this? Well, first of all, this structure allows us to multiply pure powers of 2 by pure powers of 3. I'm going to call this, even though it is multiplication, I'm going to give it a separate name. I'm going to call it g of xy. So it's just x times y, but x is a power of 2, and y is a power of 3. And how can we do this? How can we say that z is equal to g of xy? Well, we simply need to say that v2 of z is equal to x, and v3 of z is equal to y. And finally, we require that z is the smallest such number that satisfies these projection properties. Remember that we can talk about less than or equal to because we're working in the natural numbers with addition. We can use this restricted multiplication to square powers of 2. Again, I'm going to describe this as a function with a restricted domain. And the process of squaring a number is simple. We simply take x and then find the smallest power of 3 that's larger than it. We round x up to a power of 3. Again, we can use this v3 to recognize powers of 3. And we can talk about less than, so we can take x and round it up. We can just take the smallest power of 3 that's larger than x. And now that we have those two numbers, we have x, which is a power of 2, and a slightly larger thing, which is a power of 3. We multiply those two together. And remember that we could multiply powers of 2 by powers of 3. And then we take the result. It's not quite going to be the answer that we want, but it turns out if we round down to a power of 2, we get what we want. We get x squared. Of course, if x is a power of 2, then x squared is also going to be a power of 2. In particular, if x is equal to 2 to the a, then x squared is going to be equal to 2 to the 2a. So we can double our exponents. Let me emphasize that. We can double the exponents on powers of 2 in this particular structure. And if you unwind the connection between Büchi arithmetic and the weak second order theory of one successor, this operation here, being able to square powers of 2, corresponds to being able to double any singleton number element of the weak second order theory of one successor. In other words, having access to v2 and v3 allows us to talk about doubling in the weak second order theory of one successor, which allows us to talk about addition, which allows us to talk about concatenation, which allows us to talk about addition and multiplication, which allows us to talk about Turing machines. And so this structure here has an undecidable theory. So I hope you had fun with that. I certainly had tons of fun getting distracted looking through the literature about these sorts of questions, how we can take these structures that I really like and by adding in new things to them, make them undecidable. But I promise that in the next video, we will go back to talking about regular languages and nicely decidable things. So please let me know if you have any questions about these constructions in the comments below, if there's something that I should have explained more fully. And I hope to see you in the next video.